So, we were looking at the language of propositional logic by looking at the syntax of the language, and we had seen in the last class that the alphabet of propositional logic consists of two parts. In fact, the alphabet of any language consists of two parts. One is the logical part, which is kind of domain independent and common to all logics, and the other is non logical part, which is the part which is talking about the domain essentially. So, in our case, since we are talking with the propositional logic language, the domain dependent part is basically a set of symbols which will stand for certain statements in the domain essentially, and these symbols are the atomic sentences. So, when we look at the language, we define this as a pair where we choose a set of connectives. As I said, you can choose a subset of the connectives and a set of formulas. So, the set of formulas is chosen by first choosing a set of atomic formulas and then defining the rest of the language essentially. So, let us call this set of formulas F, and we want to define what this set is essentially, and let us call this set of atomic formulas as P. That is given to us, that is a basic unit essentially. So, this set F is defined as by structural recursion as follows, that these two symbols propositional constants that we had, they will belong to the set of formulas of a propositional language F. By definition, they are always there. Then if anything belongs to the set of atomic formulas, then that thing belongs to the set of formulas. So, in other words, all atomic formulas are formulas, or all atomic symbols stand for formulas. Then if alpha belongs to the set of formulas, then the expression not alpha also belongs to the set of formulas. So, this symbol, this unary connective that we have been talking about, we will call it as not. And finally, if alpha and beta belong to the set of formulas, then we often use brackets, but we do not always need to. So, for every binary connective that we have in our language, we can take up two formulas and connect it using that binary connective and produce a new formula. So, in this way, the set of formulas is constructed. What is the size of this set? Supposing the size of P is 5, that means I start with some 5 statements and I want to do some reasoning based on those 5 statements. The set of formulas that you can construct from that is still infinite essentially, because you can always keep constructing bigger and bigger and bigger formulas, which will combine them using different things essentially. So, this set F essentially is the set of sentences in our language. And we are interested in knowing which of these sentences are true and which of the sentences are false. Okay. So, let us talk about the truth values of sentences or semantics. Which is concerned with truth values. As we said a little while earlier that there is one notion of semantics which is as to what does it mean, but in our case in propositional logic there is nothing really complicated about that, because we have said that these are propositional variables and you can actually plug in anything you want. P can stand for any statement that you are interested in essentially. What we are interested in is that when we construct these larger and larger compound sentences, which of them will be true and which of them will be false essentially. So, for atomic sentences, or propositional variables, we have a valuation function, let us call it V, which maps the set of atomic formulas to a two valued set. So, let us use this set T and F. So, throughout the course we will use this two valued set to stand for truth values. As far as between us, we will call the first element as true and the second element as false, and we will try to associate these two values with our domain. So, whatever we think is true in our domain, we will want to map to this symbol T, and whatever is not true, we would like to map in the symbol false essentially. So, for atomic sentences, the valuation is given externally. Somebody tells you which statement is true, which statement is false essentially. So, you cannot determine it on this thing, but for the rest of the formulas, we determine the truth value using the meaning of the connectives essentially. So, we will make statements like this, that if alpha is equal to 2. This is a short form, I do not know whether we should use or not. So, let us assume we will use this short form. So, this short form alpha is equal to true essentially stands for alpha is true. To be more precise, we should have said something like val alpha is equal to true. But since we are dealing with propositional logic, we will use this short form at least for the time being essentially. When we move on to first order logic, we will see that this equal symbol has its own meaning that will be part of the language, and therefore, we will have to give a different this thing. So, this we will do for PL only. So, if alpha is equal to true, then not alpha is equal to false. So, this gives us how to arrive at a truth value of a sentence which is made up using the negation sign essentially. So, you are familiar with this idea of truth tables. So, we can construct a truth table for negation. So, we can say alpha is true or false, then not alpha is false or true. Likewise, we can construct truth tables as you are familiar with for other connectives. So, let me do a few examples here. So, the other connectives are binary connectives. So, they take two values. So, let us say alpha and beta, and the values are either true true, false false, or true. These are the four combinations of values that we can look at, and we can define different connectives. So, what is the meaning of alpha and beta? So, no doubt you are familiar with this. We read this as and the semantics is defined as both the constituents must be true. So, whenever both are true, this is true, in all other cases this is false. Alpha or beta, this is or, and it is the inclusive or. So, if either one is true, this is true, else it is false. Then let us do a couple of more equivalence. So, when I write equivalence here, it means alpha equivalent to beta. So, both must have the same value, in which case it is true. When both have the same value, it is true, and otherwise when they have different values, it is false. The exact opposite of this is the symbol of XOR or exclusive OR, which is true only when they are both different, and it is false otherwise. So, you can see that between XOR and this equivalence, they are the complement of each other essentially. So, from this you can kind of guess that if you have a formula of the kind not of alpha XOR beta, then this must be logically equivalent to alpha equivalent to beta. So, the point of this exercise is to show that you can say the same thing in different ways, even in a language like logic. You want to say that both alpha and beta take the same truth value. You can either use this simple expression which actually says that A alpha is equivalent to beta, or you can say it in a slightly roundabout way, which is that not alpha XOR beta essentially. One equivalence that we will often use is that instead of saying that alpha implies beta, we can say not alpha or beta. So, I have not defined implication here, but I will leave it as a small exercise for you to define implication and the other this thing. So, the question that we can ask is how many binary connectives are there. Because you can fill in this column in 16 different ways, we can actually have 16 different binary connectives, and the next question is, do we need all of them essentially? So, the question that we are asking is how many binary connectives do we need? So, we just saw an example in which we said that if you have alpha implies beta, then you can actually replace it with not alpha or beta. They will have, and you should do it as a small exercise, construct the truth table. Likewise, if we have alpha and beta, then we can actually replace it by. So, let me use the standard notation is equal to not alpha and beta, which is equivalent to not alpha or not beta. So, the interesting thing is that we can do away with these two symbols, we can do away with implication and whatever we wanted to say with implication, whenever we wanted to say alpha implies beta, instead we could have said not alpha or beta. Likewise, whenever we wanted to say alpha and beta, we could have implemented, we could have said not of not alpha or not beta. So, the exercise is show that the set of negation and or is complete. What do we mean by complete? That everything we can say with other connectives can be said using only these two connectives essentially. So, there is a notion of completeness in the choice of logical connectives that you use, and what people were trying out a long time ago was trying out different combinations of connectives and trying to say which is a good set to work with essentially. So, as we will see a little bit later, when you look at Hilbert systems, they work only with implication essentially, only one thing. But the thing is, of course, implication is not complete. So, you can only do certain things with Hilbert system, but then we will look at also Frege's axiomatic system. And Frege actually showed that this set of negation and implication is complete, which means that anything you want to say using any of these binary connectives and negation can be said only with negation and implication essentially. So, other sets which are of interest to us and we will see later is this set of negation or and which we will use in one of our proof procedures. Then you would have heard about NAND and NOR. So, these were known as Sheffer's stroke and Peirce's arrow when they were, because they were shown by Sheffer and Peirce. These are single connectives. This NAND is actually equal to not of AND. So, if you take the AND truth table and just flip it, you will get NAND, and NOR is not of OR, and it has been shown, and those of you who have studied Boolean circuits would know that the NAND gate and the NOR gate are enough to construct any circuit that you want, which also means that anything you want to say in propositional logic can be said just with the NAND gate and the NOR gate. Only one connective is enough essentially. One more question which I want to ask is, what about let us say ternary connectives and other higher order connectives? Do we need them? Do we need something which will say that I want to connect 3 formulas to form one compound formula essentially? Because all the connectives that we have seen are binary connectives, they take 2 formulas and give you one compound formulas. What about taking 3 at a time or 4 at a time or 5 at a time? Can we say something more than with those things? Again, we will not go into the details, but it has been shown that everything that you can say with higher arity connectives can be said with binary connectives, and everything that can be said with binary connectives can be said with any of these sets which is complete. So, NOT and OR is complete, NOT OR AND is complete, NAND is complete, NOR is complete, and this thing. So, we can use any of them essentially. Okay, so, what we have done now is to define a language essentially, and we have said we started with an alphabet. The alphabet consists of binary connectives, and as we said we can choose a subset plus a set of propositional symbols, and then through structural recursion we have determined the set of formulas that can be expressed in that language essentially. Then we looked at the semantics, and we said as to how do you determine the truth value of a sentence essentially. Okay. We did not write it explicitly, but we will have statements like if alpha is equal to t and beta is equal to t, then alpha and beta is equal to t, else alpha and beta. We could have said statements like this. So, which means that for any given formula you can determine its truth value based on the truth value of the inputs. So, let us say that we have a p is equal to t and q is equal to false and r is equal to t essentially, and this is a set that we are given. So, we are given 3 propositional variables, and we are giving a valuation function which says p is true and q is false and r is true. Then we take an arbitrary formula, q implies r or r implies p, and the whole thing is equivalent to r or t. So, some random formula I have written. The question that we would like to ask is that, and you know that we can construct an infinite set of formulas like this. So, given any arbitrary formula like this, the question we are interested in is this formula true or is this formula false, based on the fact that we have been told that p is true and q is false and r is true essentially. So, we can now of course break it down. We can see that r is true. So, sorry, I do not have a q, I have a, though I could have used the top symbol, but let us just use something simpler. Q. So, we said that this is false and r is true. So, this formula by the semantics of OR is becomes true, because at least one should be true. Then Q is false, and if you look at the truth table of Q, you will see that whether R is true or not, it does not really matter, but this becomes true. Now, since this is true, this whole formula is true, irrespective of what is the valuation of R or P, because it is a OR connective here, and because this is true and this is true, this whole formula becomes true. So, we can take any arbitrary formula and evaluate its truth value by plugging in the value of that essentially. But this is dependent upon the fact that we have been given a valuation function. So, for this valuation, so in general there are three kinds of formulas. Remember that we have defined this set of formulas given a language essentially. This set is basically partitioned into three kinds of formulas. One is called tautologies, which are always true. And this is determined by the last column in the truth table has all T's essentially. If you construct the truth table for that particular formula, then the last column in the truth table will always be T's, and such formulas are called tautologies. So, examples are, no doubt you are familiar with such things. P or not P, obviously since one of them has to be true, or P implies P, which you will recognize is the same formula said in a different way, and so on. There can be many tautologies actually. Then we have contradictions, or unsatisfiable. These are formulas which are always false. So, when you look at this statement here, for this one it will be all F's in tautologies. In unsatisfiable formulas, they are always false, irrespective of what valuation you choose for the constituent atomic sentences, that formula will always be false. And again you are familiar with formulas like this, P and not P is a classical example of a contradiction essentially. The third kind of formulas are known as contingencies. True in some rows. Which is equivalent to saying true for some valuations, because each row in the truth table corresponds to a valuation. You are saying P is true or Q is false or R is true or false. So, each row corresponds to a valuation, and contingencies are formulas which are true for some rows and not all rows essentially. So, example, we also call them as satisfiable formulas. So, strictly speaking, the set of satisfiable formulas also includes tautologies essentially, but we can find a valuation which will satisfy the formulas, and an example of that is P implies Q, a simple formula which will be true in some rows and false in some rows as indicated by the truth table itself essentially. Okay, so, this defines the syntax and the semantics of propositional logic. In the next class, we will look at proof methods as to how do we arrive at these truth values through different process, which is the proof process essentially.